So we'll do C and we'll do example 6. This is a really good, I know I don't know if, I want to say there's a question similar to this on the test coming up next week. In part B on Friday, the question said, show that there is a point P where it's the next coordinate of 3 that has a horizontal tangent line. In finding that, you're also finding a critical value, right? So they didn't use that terminology there, but you've already found a critical value. And then the follow-up question is going to ask us about a local maximum, local minimum. And to describe whether you have a local maximum or local minimum, you first need to find the critical values. So we've already done step 1. And then we need to use either the first derivative test or the second derivative test. The first derivative test is kind of what we did in the past because we were able to make a sign chart. But on Friday, I mentioned that if your dy dx involves 2 variables, sign chart's kind of out the window because you need to be thinking, I shouldn't say it's out the window, unless you have some sort of other information that locks the sign of one of the variables. Sometimes they will say something like y is greater than 0. You're back in it with the sign chart on that one if like you knew y was greater than 0. I don't believe we had that here, did we? Nope. So short of like knowing something about our function, really that's when the second derivative comes into play. They're asking us to find d squared y dx squared too, so they are leading us to the second derivative test. So in general, I was over talking there. If you have x's and y's in your dy dx, especially in your numerator, because that's where 0 happens, then it does make it hard to write, it makes it basically impossible to make a sign chart. So let's find our second derivative and let's answer our question. So where is our derivative? There's our derivative, 3y minus 2x over 8y minus 3x. That is going to be a quotient rule problem. So d squared y dx squared equals 8y minus 3x but squared. And then we can go derivative of the first. So 3 dy dx minus 2 times the second times 8y minus 3x. Minus, just flip that. So I'm going to do 3y minus 2x. And then 8 dy dx minus 3. So letter C, we need to answer the question. It says, find the value of d squared y dx squared. I started saying this on Friday or when we first started doing this, and I jumped the gun on it a little bit. Normally, if I had to find d squared y dx squared, I need to plug back in for the dy dx. But if I just need to find the value, I can leave those there because my goal here is to get a number. And I know that dy dx at the point from part B is 0. So when I go to plug in here, those dy dx's, because we're going for value, equal 0. So I'm going to leave this as is. Really the dividing line is, if they want to know what d squared y dx squared is, I've got to have it fully in terms of x and y's. If I need a value, leave the dy dx in place. You might even have that value already. So again, from Friday, our point was 3, 2. So the next thing I want to do, and I think I can zoom in a little bit here now, d squared y dx squared evaluated at x comma y equals 3 comma 2 is going to be 3 times 0 minus 2 times 8 times 3 minus 3 times 2. Then here I'm going to have 3 times 2. I have those x's and y's backwards, don't I? In my first part. It should be 8 times 2 minus 3 times 3. It's y minus x. 3 times 2 minus 3 times 3. Oh. Okay, 3 times 2 minus 2 times 3. Hey, that sure feels like 0 too. Times 8 times 0 minus 3. And all of this is going to be 8 times 2 minus 3 times 3, but squared. Do you guys agree? I fixed the mistake that I found. Did I do anything else? Okay. So the nice part about this right here, this is 0. So this is 0 times negative 3. This whole thing is just 0, right? So if you spot anything like that, if you spot something that's a 0 being multiplied, you can save yourself a little bit of calculation work. And really, I just have negative 2 times this over that same thing, but squared. So this is negative 2 times 16 minus 9 over 16 minus 9, but squared. Negative 2 times 5 over 25, which is negative 2/5. You can cancel the 5 and the 20. You can, honestly, any one of these three answers is fine. The only thing you need for the rest of this problem is to know whether that thing is positive or negative. I got from here to here by just simplifying the fraction 5/25. 5/25 simplifies to 1/5. Did I screw something up? It is. I did, what did I do? I did 16 minus 11. I was 1 off of 10. Thank you. So not much of a difference. And big difference. But I'll put a 7 there. I'll put a 49 there. And I'll make my overall answer negative 2/7. For the same reason that 7 over 49 simplifies to 1/7. Thank you, Parviz. Which speaks to the idea of, if you can tell what sign it is, you have a positive denominator, right? Whether you do the math right or wrong, you better have a positive denominator because you were squaring something. And then you were multiplying negative 2 by 16 minus 9. So if you leave your answer there, you can tell whether that's greater or less than 0. And, you don't lose a point if you don't bother going further. And if you go further and do my silly mistake, then you lose a point. So, okay. So the question says, does the curve have a local maximum, a local minimum, or neither? Justify your answer. And then we're just going to use the second derivative test. So we found out that our second derivative is negative. Is that local min or local max? Local max, right? That's the reverse association. The only time it's a direct association is when you're talking about the concavity. Otherwise, you're going from concavity to something else, and it's reverse. It's not what your instinct would tell you. So we're going to say the local maximum, and we've got to list all of the conditions of the second derivative test, which are that dy dx evaluated at the point x comma y equals 3 comma 2 equals 0, and d squared y dx squared evaluated at that same point is less than 0. I don't think they're taking off the point because of the word because, but that's what should be there. So a little bit tedious, but nothing crazy difficult. You don't really have to do any algebra with the second derivative there. You just need to plug all the numbers in. Look for zeros to make your life easier. All right. Okay, last two examples. Jumping right past the fact that, you've got to find the derivative. This one starts with it is known what dy dx is. Show that the curve does not have any horizontal tangent lines. I think this is an interesting one. We have our curve. We have a dy dx. Can dy dx equal 0? Can I find a y or x value that makes this 0? Yeah, y equals 2. So something's going to go wrong when we try to plug 2 back into our original equation. Basically, what's going on here is if we graphed this graph would never touch y equals 2. Or it would never cross over a point that had a y value of 2. And we'll look at that when we're done doing the math to show it. So basically what I would write here is dy dx equals 0 because they said horizontal tangent line. And then I would say y equals 2. Kind of setting my problem up. If I have a horizontal tangent line, my derivative equals 0. The only way that's happening is if y equals 2. Let's plug y equals 2 into our curve. So we end up with 6x minus 3xy. How about we say minus 6x? There we go. Y. 6x. No, not y, because I plugged the 2 in. Plus 8 equals 40. Oh, this was easy. Those 6x's cancel. The only way that this could have a horizontal tangent line would be if 8 equals 40. And last time I checked, 8 doesn't equal 40. Might just make a conclusion. There are no points on the curve with a y value of 2. So again, we see that, when you don't have anything left to do, you usually go back to the curve itself. I think of your question from Friday, Alicia, like, how did I know to plug that into the curve? Well, where else do I plug it? And kind of so it is really common to go back to the curve. You didn't know there were any horizontal tangent lines. You didn't know how it was going to happen. But then once you plugged it in, the 6x is canceled and you didn't have anything left to get an x value out of that. Show that the curve has a vertical tangent line when y equals -2. A vertical tangent line means dy dx is undefined. That means that y squared minus x, the denominator, equals 0, which means that y squared equals x. There's a couple different ways you could go with this. You could just, I think there are a couple different ways to do this. And if you have something different that pops to your brain, we could plug that -2 in right now. Since that's so simple, y squared equals x, I'm going to go back to the curve and I'm going to plug y squared in for x. Again, like I said, there's a couple different directions you can go to this. That will give us 6y squared minus 3y cubed plus y cubed equals 40, which sounds like 6y squared minus minus 2y cubed. Oops, wrong button. And now when I plug that -2 in, I think this is going to give me 40. So we've got 6 times 4 minus 2 times -8 equals 40. And we end up with 24 plus 16. And then I will say the curve what was x if x equals y squared? What's y? What did they tell us y was? Yeah. So what's x? 4. So I showed it. Basically, what this math is showing here, this is the math showing that that point is on that line. Maybe I should have solved for that x first and just plug them both in. I think that would make a little more sense from a teaching perspective. It's been a while since I've done this problem. I probably could have jumped to that question that I asked here and then just plugged x and y in. For some reason, my brain was telling me that it was going to make more sense going the other way, but I think that's what I should have done. If y squared is x, then x is 4. Plug them both in. The key is if you have a point and you want to decide if it's on the line or not, you have to plug it in and see if you get a true statement or a false statement. Cool. I guess before I let you guys get to work, I'm going to throw this into Desmos just to see that both of those two things are true. Our function was 6x minus 3xy plus y cubed equals 40. I'm in a weird zoom. Yeah, there we go. So we do have a vertical tangent line there at the point 4, -2. And as you can see, there are no horizontal tangent lines. There's a horizontal asymptote here, but that means that the line never really does get flat. And yeah, you can keep zooming out, but I think we have pretty much, wrong way. We pretty much have the whole picture there, but no actual horizontal tangent lines.